Hello, everyone. The last session. I'm Gennadii Donchyts, so I'm short Genna. So I'm cloud geographer at Google. I'm based in Europe, in Netherlands. So I work mainly in IMEA region with commercial customers and governmental customers of Google Earth Engine.
Hi everyone, I'm Kel Markert. I am also a cloud geographer. My role is working primarily with US public sector agencies here in the US. I hope everyone's wide awake after a long 3 days. We have our link for the slides up there. You can also probably get the slides from the agenda. If you want to grab those slides, there's links to code and everything, and we'll be walking through a little bit of code throughout the session.
Yes, thanks, Cal. Let me explain the first logistics of this session. So you see the title, it's a way of water. So we will talk a lot about water today. And how this session is organized is that first part will be mainly lecture, or I will be just showing some examples of different water applications which we were working on. And then after that, what we will have is more like follow-along session, which will basically go through like simple water mapping or quantifying surface water change of water body using different algorithms. So I'll just basically walk you through some of the steps that you could do. And feel free to open slides, and then you would click at links on code and then just run this code, or you can just listen. So anyway, either way would be good. And Kel, you will be helping. So if you have any questions, you can raise hand. Kel will help. Another option is to come to the microphone and then ask your question there.
Yep. So I'm going to be exit stage left, and I'll be out there in the crowd. So just raise your hand, and I'll run over and see what I can do to help. Thanks.
Yep, thanks. Okay, this session will take 1 hour, so we have 3 minutes. So I think let me jump to the next slide and give you an overview of what we will be doing today. So as I mentioned, the first part, we will have a look at different examples of surface water or water-related applications. These are not all for sure examples. So there are plenty. I think there are probably hundreds or thousands of different examples where Earth Engine is used in the context of water, or different data sets used in the context of water. But here I will just show you some variety of examples looking at coastal applications, agriculture maybe, or some more general like academic studies, and some links to the paper. So many slides, they also have links, so you could also open it later and study. But that will be the first section. And then after that, we will get to the more practical session. So this is basically what I mentioned on types of applications that I will be presenting here. Then if you look at water, of course, why water? Personally, it's a topic where I worked on for many years using Earth Engine, applying different remote sensing methods, as well as Kel. So that's the reason why we also co-leading this. So we have frequent discussion about different applications of related to water using remote sensing. And if you look at types of problems you can address with Google Earth Engine, it's really enormous amount. And in sometimes for areas where you have a lot of water stress, they would be more relevant. So if you have, let's say, droughts, water stressed regions, then understanding how much water you have and monitoring this is of course important. When you have too much water, it's also bad, so you get floods. We have agricultural applications with existing satellites, so looking at the optical radar missions, we can monitor how much water content we have in vegetation, in crops. So we saw many examples also like OpenET, which demonstrates the value of this type of water-related data sets derived from remote sensing data. So it's really plenty of applications, and they, of course, capture different parts of what we call water cycle, so water in different stages. Looking at, let's say, one of applications, of course, floods. So that's on the left, you see some animation of flood water occurring in Europe in 2021. So there was a huge flood. And with Earth Engine, I was able to map the surface water or flood water in about, I think, 1 day it took to really mobilize and get most recent data. And this was really picked up as information which nobody knew where we had floods. So it took really several days, like the agencies which were responsible to map this water, they did not expect this flood as this scale. And so that was like really demonstration of, okay, this tool really can help to get insights in time. So another example, if you look at on the right slide, so it's a severe Mekong, maybe some of you heard this application. So Kel worked quite a bit on that. Maybe, Kel, do you have any comments on this?
Yeah, before I joined Google, one of the challenges in Southeast Asia were they experienced flooding, large-scale flooding every year due to the monsoon. And so they needed some service around there to where they understood that, here are floods happening, right? And they didn't just want to, have some map 5 days later on where floods have happened. They wanted to say, we have a satellite acquisition and we want that, as soon as possible, right? So that's where the hydrologic remote sensing analysis for floods, or hydrofloods for short, some of our colleagues here from Severe and the Southeast Asia region are actually implementing this. And so it's like a sensor agnostic way to bring in different sensors from Landsat, Sentinel-2, Sentinel-1, and start deriving a lot of these surface water maps to deliver in an automated fashion to these disaster management agencies.
Thank you, Kel. And here, many of you heard about the cloud-based remote sensing with Google Earth Engine book. So it actually has a chapter which Kel and I and a few other people co-authored focusing on flood water mapping. So there are some links you can find in this slide deck to look at, to study more after this session. And yes, this is just some nice example. I think many of you probably saw this. If you look at time-lapse or the multi-annual changes on a globe, on Earth, you find really some fascinating examples of how water behaves, like in this case, rivers. If you zoom in maybe to Brahmaputra, then you see like braided rivers. This one is a meandering river where basically it bumps into the city. So I would be really interested to talk to these people who did water management or protection of that city, what you see there. So there's like when you start exploring surface water changes on more interannual, there's really plenty of examples which are just look like art. So this one, we are looking now in Myanmar, and again, it's a multi-annual, so interannual average composite image what you see here over years. So basically every year they were constructing new reservoir. And there, you think, question whether it's actually positive or negative change. But if you look downhill from this constructed reservoir, you see that before reservoirs were constructed, this land looked more yellowish. And then once after they were constructed, it looks a little bit more darker. And what we see here, it's a false color composite image. So these are not RGB colors, of course, it's infrared, shortwave infrared. So when you have water or moist, let's say, with the land cover, it absorbs in infrared color, it absorbs light much more than in other invisible bands, and then you could detect basically this more wet areas easily. And in this case, I think it was very positive, at least in that part, that these water bodies were constructed. But quantifying, detecting these changes automatically, that's could be a challenge. And so this is an example of applications where I used Earth Engine to actually do processing globally. So it was part of when I was doing PhD with Google Earth Engine. So basically develop algorithm where you can map this long-term surface water changes using leveraging Earth Engine algorithms and dataset, in this case using Landsat imagery. And the algorithms themselves, they are relatively simple, and that's something where, which if you manage to make this, express your algorithms methods in a way that it would not require much computing in Earth Engine, then you can really easily scale it globally. So I could repeat this kind of algorithm, running it for I don't know, 100 times probably to do global study. And the method is really was developed in a way that you would create like annually average image, a composite image, so compute the same statistics using all available images for year to get rid of clouds or cloud shadow noise. And then once you start looking on anomaly change between these different images, you could compare separate images, but you could also use methods like linear regression. That's what I used in this algorithm. And basically doing like annual average image compute and then computing linear regression over this let's say, the time range. You would be able, looking at the slope of this linear regression, you will be able to actually map this type of changes globally or locally. So that's like one example. And this was also summarized to look at where did these changes, where did we have most changes happening. So I was able to identify like that RLC, for example, this is the largest area where water disappeared. There was also, we looked at the coast lines as well, but in some areas there was like places like Tibetan Plateau, we saw like huge amount of new water appearing. So there was like some academic basically study with this tool. Another very important data set and study to mention is that probably many of you heard of GRC surface water data set. And that's something what's available in Earth Engine. And basically what this data set consists of is that you get like a monthly water occurrence data, so monthly water mask based on all images measured during 1 month. So they were able to basically generate images where you have water, non-water, or no data pixel values, so discrete kind of image. But then having this image for every month, you don't have to detect water from raw satellite imagery, so you can basically start using this. So this is really a very good data set to get kind of insights where you get not focusing on very much on accuracy, or the accuracy in this case, it's very good, but if you really need to look at the local kind of water body, maybe different features, then this would be just good as a starting point. And yeah, here's just example of visualizing this data set over, I think it's the same probably place where we looked at the beginning at Time-Lapse. And I mentioned that coastal application, that's another type of study you could think of where this type of data set would be very useful. So this is another paper we published focusing on the coastline changes. With similar algorithm as before, there are many studies looking more deeper in these coastal changes, for example, looking at intertidal bathymetry mapping or water occurrence mapping, so where you could basically use water boundary to as a measurement instrument in this case. Because if you can detect for different water levels at different images, we can detect water mask, water boundary, and then combining this from different images, then you could basically compute the statistics of or distribution of, let's say, this water pixels over the coastal or intertidal range, what's called area. And if necessary, you could actually calibrate it, turn it into depths, but then you would need really elevation data for that. If you look at similar application focusing on bathymetry, this is for Dutch area, so that's something what I was doing some few years ago. This is type of images that you would be working with. So it's really, noisy images, most of them. So you have clouds, you get shadows, you get waves, and sediment water. But with what's nice about Earth engines that you could do all types of multi-temporal analysis. So you could get rid of this noise, and if you develop proper algorithms, then you can basically filter this, disintegrate all these different events or features and then really focus on what you're interested in. So what you see here, it's a result of analysis applied to that previous time-lapse. And then as a result, you can get intertidal bathymetry or intertidal water occurrence, you can call it. There are methods also that you could look even at, let's say, underwater. So in some cases, even in this very cloudy area and relatively turbid water as a North Sea. So I could not see like seabed there when I go and walk in this area. So yeah, I live very close to this area, to North Sea. But it appears that we can also actually, sometimes there are sunny days, and during the sunny days you can see seabed up to 20, I think even 30 meters. And by knowing really how physics works or how water light gets absorbed in different bands, spectral bands, you can actually quantify this seabed signal, and then combining it over multiple years, you will be able to actually reconstruct even, let's say, look how this seabed looks like or how depths look like in different areas. And what's nice about this tool or this type of algorithm is that you could then apply it over multiple time intervals, so you can basically capture even dynamics. So if you will be able, so if your water looks sometimes is transparent, then with Earth Engine you can basically do this type of applications. OpenET, we saw presentation before in one of the sessions. There are many other data sets related to water, like you have precipitation, of course, reanalysis, both reanalysis and also data coming from different meteorological satellites, for example. There are also forecasts like GFS, so we have if we want to build, for example, application looking at weather, Earth Engine now every 6 hours we have data set where you could look at for 2 weeks in the future, you get weather forecast data with precipitation estimates and temperature and other data set. Another interesting data set which we see also used a lot in agriculture or being picked up in agriculture is a SMAP data set. It was actually a satellite which had active and passive sensor. I think active sensor broke at some moment very quickly. But even with, what's nice is that even from this passive sensor, so it's a microwave, I think wavelength allows also to see like signal coming from basically to quantify soil moisture from with this data set. And it's, I think, I don't remember what was the specific wavelength for that data set, but it's able to actually see the root zone and surface water also, or moisture on a surface. And I think it's the frequency or revisit frequency is quite high, so you can capture all kind of, I think even between less than a day frequency, capture how moisture was changing in this area. And here, last example, what I wanted to show is more focusing on zooming in to specific analysis of specific water bodies. So of course we have rivers, lakes, and kind of smaller inland water bodies. In this study, I developed algorithm where I try to quantify, actually make use of all available optical satellite imagery in Earth Engine to quantify dynamics of reservoirs, so man-made reservoirs. And what you see on this image, on this slide, is actually the seasonal variability of these reservoirs. So if you would take time series of this area change of every reservoir and then try to decouple it, let's say, trend of this change and also seasonal components, then and then compute statistics of seasonal component, you would see then this type of let's say results where you see that like in India, for example, so red pixels in this case, they show, color shows that there is a lot of dynamics, and blue means there is less dynamics. And if you look at the trend component, then this shows basically on which reservoirs we had like large interannual changes. So you see that some reservoirs, so there's one example here, it's in Al Masira reservoir in Morocco. You see that between years there was large change. then you can see it on this image. And this paper has many more details, also as well as algorithm explaining how this everything works. There's also app support in this paper, which is you could, if you open slides, and you can open under this link, where you can zoom in on any of this. I think it's 72,000 reservoirs, both a bit larger and smaller. And when we zoom in and then click on any of these reservoirs, then you will get this time series of surface water area queried. And it's not very documented there, but you could actually click on these points and then get the actual satellite imagery. So it's really a more academic study, I would say. But you can imagine that this can be also brought into in the context of water management. So basin water management, if you really can control, let's say, how you can change this releases from this reservoir, so you can try to actually optimize water use, hydropower generation, and use maybe of water for irrigation. So there are multiple applications where this type of data sets would be useful. Zooming into, I see that I ran a bit over time for this introductory part, but we will catch up then in the next slide. So zooming in on how this algorithm works, it's quite, I would say, sophisticated. So there are multiple steps involved, both related to water detection. So basically taking every optical satellite image, so it's a multispectral image, and then mapping water which we can see. But these algorithms actually also make use of images where we see only a small part of this water body. And then it tries to fill in gaps and guess, actually based on historical data, tries to actually fill unseen pixels. So there's multiple steps involved. In the next sections, we will try to generate something similar to what this algorithm does, but only involving like few first steps. So computing surface water mask, and then trying to quantify this derive this as time series from multiple images, but not including this more what's called dynamic thresholding method and also gap filling part. So just to get feeling like how you would build something like this. And what you see on top is these are all images selected for this test reservoir over some periods. I think it's 1 year. And you can see that some of the images are cloudy. So what we will learn also in next steps is how can we detect these cloudy images quickly and also filter them out. Because of course, if your image is reservoir fully covered by clouds, it makes less, you cannot use it to detect anything there. If you look at how this algorithm described in this paper works, you see on the left side these are the actual images used to do this detection. And on the right hand side, you see basically the detected surface water area. And you can see also that when there are clouds or shadows, we still see water area so it sees under clouds, let's call it that way. So there's no like AI involved method, but it's more Bayesian-like approach to try to make use of historical water occurrence and current water that we can detect and infer basically how much this water body is filled, assuming there were no large like morphological changes happening in this reservoir. Okay, so that's more, let's say, I would call advanced, so we won't be able to develop this fully. The next part is will be a section where you can actually follow along. So what we have is, so this section 2 is will demonstrate how you could generate surface water area time series for one test water body using GRC monthly water occurrence data set. And there are actually tutorials also available to do this you could find in the user guide, but I will try to show these links here as well. So actually here is an example showing where you can find this data set. So we will be using both mainly monthly water occurrence data set, but there's also another, if you type GRC in a data set search in Earth Engine, you'll see that there's like a number of data sets available there. So the first one, the global surface water mapping layers, it's also very useful. So we see it also in the next section exercises. And here you could see also on the right, so if you in the open documentation in the Earth Engine, there's actually a section where you could get more documentation explaining how to work with this GRC surface water dataset. So there are a number of tutorials available which you can just copy paste and get like more insights from this data. So if you look at the scripts that presented here in these tutorials, they basically starting from very small ones, and then they build up to something more advanced, at least like in every section. So here, if once we reference this data set, I found out that like by default, it's also the data set, if you click at inspect this values what you have there, there's also mask used in this data set, which makes it like half transparent. So it actually needs some reworking a little bit to get it to the unmask values and really to try to use, let's say, in your computations. So and that's what you see on the code from lines here 10. I hope we can see, yes, can read the text or the code. So from these lines 10 to 14, you see that there is some manipulation done with this data set to make it smoother and remove or convert it to values which would vary between 0 and 1, because by default it's scaled from 0 to 100. I think to save space probably. So, and then these scripts, what you will see in this slide deck, then they would, like if you click on the, so on every slide where you see code, you can click at the code and then you will get code editor open with a script which corresponds to this section. So here we see in this script, basically after these manipulations, it also adds color palette, so we could visualize this water occurrence. So that's water history or water occurrence, which was computed based on the 30 years, I think maybe a bit more than 30, so from 1984 until now. So GRCs that generated like statistics of every, let's say, water body on Earth, which they could detect, and they generated statistics of water occurrence. So what is the percentage that this area was covered by water, independently of time? And then that's frequently very useful data set to start, let's say, inspecting your water body. So if you map this here, you could also try adding, let's see if I go to the next slide. You can also visualize it in different ways. So here it's the same data set, but then visualized in more realistic way. So we added like hill shade to this data set, and I added basically isolines for every like 10% of change in this water occurrence, and like just visualize like, okay, if this reservoir would be filled 50% or 10%, how it will change. So these are some kind of experiments you can do with this data set, with the water occurrence. But if you look at so water occurrence is just one image which shows this water probability in every pixel. But if you look at another data set or the second data set which I listed there, it's a monthly water occurrence. Then, and if you show these values or these images present in this data set, this is more or less what you will see in the data. So basically in every monthly average image that you have derived from Landsat, the GRC, the authors, they generated this kind of image, binary image, or it has like 3 values. And so if you animate this, then that's something what we would be able to observe. And imagine that when you would want to quantify this data and or quantify surface water area change over this water body. If you know the water body boundary, then this is like 101 of Earth Engine tutorial that you would need to apply here. So basically for every image you would have to compute, let's say, how many pixels you have, what's the area, total area of pixels covered by water, and that can be done, of course, with by combining the pixel area with regional reducer. So we see this like in the middle of the script. Once you map this function over every image and you know your limited boundary area, you will be able to just add this computed property and return back, and then we can just plot chart, and that will be our quantified surface water area. So this is like trivial way to detect water dynamics if accuracy, what you will get here, would be sufficient. Moving to next part is, so with GRC, that's what you would recommend, like really starting always, if it covers your, let's say, time range that you're interested in studying and the accuracy is sufficient, this is always good starting point. Actually, in the paper, what I mentioned in the last examples, analyzing reservoirs, I'm using this data set, so the water occurrence data set, as to fill in gaps. So I'm not recomputing it from scratch. And that's the example of how useful that data set also is. So it's good also to combine, not just derive always it's from raw data, but combine existing data sets we have in Earth Engine, and in some cases maybe refine it using raw satellite imagery. When you're working with optical, multispectral satellite imagery, the water detection becomes a little bit more, not more challenging, but given that we have clouds and shadows, so it might be quite challenging in some areas. And then, but in general, the water detection is in the multispectral satellite imagery is relatively simple task if you have cloud-free image. So you would be computing different spectral indices which you can apply to really detect water based on like the basic remote sensing knowledge. So I will, in next slides, I will show some of the algorithms that I used to do this. So if you look at what type of data we have in Google Earth Engine, there are sometimes, so of course we have data sets which are higher level, but most of the data sets are multispectral satellite imagery. So we have like Landsat, Sentinel-2, maybe even MODIS and other data sets. All of this can be used also for this exercise. In next sections we will, or next slides, we actually will use only Sentinel-2 imagery. But if you want to really increase the temporal resolution of your analysis, then it makes sense to combine Landsat, all Landsat missions, and Sentinel-2. So when we talk about the, let's say, multi-spectral analysis. Of course, we have also images coming from Sentinel-1, so these are radar satellite images. The theory to detect surface water there, it would be a bit different. And that section I mentioned in the book, in Earth Engine book, what Kel authors, that actually explains, it's a good example to look at, okay, how do I detect water in radar satellite imagery? But we won't be covering here. The radar satellite imagery usually is much more useful when you observing, for example, floods. So when there are active floods, optical imagery is useless because you have area covered by clouds usually, except if flood really takes long time. But multispectral, it's a kind of good starting point. And again, it's good to understand, let's say, what these satellite missions or satellite instruments actually measure. So what are the spectral bands that they have? Special resolution, of course. So if you look here on this slide, what you see, it's an overview of the spectral bands of different missions or data sets present in Google Earth Engine. So the top row shows Sentinel-2 spectral bands. These different boxes, what you see in this slide, is the height of this box. It basically shows you the spatial resolution of satellite, while the width of this box, it shows what wavelength range is covered by different spectral bands of the satellite. So you can see that like Sentinel-2 has quite high resolution for infrared band number 8, and also visible bands, they have a resolution of 10 meter, while let's say shortwave infrared bands, so band 11, 12, on top they are they're 20 meter resolution. And at the same time, if you look at the Landsat 8 instruments, then they are quite consistent in visible bands, while there's a bit more thinner wavelength range covered by Landsat 8. Landsat 9 is not shown here, but it's kind of has similar spectral properties, or the spectral bands as Landsat 8, I believe. And like combining all these sensors, that would make sense really to increase your, let's say, temporal resolution, not just for water studies, but for any type of studies, I think, with Earth Engine. Looking at the simple theory, this is a really basics 101 remote sensing what we show in here. And so, of course, all materials, they have different spectral signatures, so they reflect light in different wavelengths differently. So for water, once it comes to infrared bands and shortwave infrared, light is absorbed, and by knowing this theory, we can basically compute what's called normalized spectral indices, so ratios which are normalized. So we will take values of these bands and compute compute ratio between, let's say, subtracting values between different bands and divided by sum, and that's one of the most used indices also for detecting water. It's called NDVI. So we take green band, infrared bands, and then you could apply, and then you would be able to detect water. Except, of course, if you focus in more higher accuracy. So sometimes you have like turbid water where you have a lot of sediments, then what you will see is that infrared bands start reflecting a lot. While shortwave infrared band, it won't be reflecting. So things become much more difficult if you want to get, let's say, last 10, 20% of accuracy and really zoom in a lot. But that's not something we will be covering today. And you can see that when we compute this NDVI index, for example, from the top image on the right, then what you see below, that's what we get. So we get basically highlighted, I think colors here inverted, but we get highlighted values, so higher values where there is water or something moist on land surface, and other values, they will get values below 0 usually. And the same way, actually, the vegetation and other indexes are computed. If you look at the same water body that was used in the previous example where we used GRC surface water data set, and just, again, eyeballing is looking at your images. This is first thing what I always do when working with Google Earth Engine. And even like animating these images, showing like, okay, how does this surface or how does signal what we observe change over time? It's always very useful to like build your hypothesis and then develop your methods. And repeating this constantly, even if more like the derived data, it's visualizing every step of your algorithm. It's something very recommended because just based your conclusions only on statistics, it's for me at least doesn't work. So I always like to look at the data at every stage of when developing algorithms. So what we can see here is that there are still quite some images cloudy over this water body. So typically, if we would work with multispectral analysis, we would use one of cloud mask algorithms. So there are plenty available. We saw also a new one announced with CloudScore Plus, I think it's called, where we use deep learning to detect these cloud images. So those are very useful, but in this exercise, we'll try to use actually something different. And so again, looking at different cloud algorithms, detecting clouds is still also quite easy task or relatively easy, unless you have like cirrus clouds or you get clouds which also cast, or thin clouds which just would deform your signal a little bit, and then everything starts to look a little bit different. But in case of water, actually, and NDVI, even when you have thin clouds, it's still able to see water quite clearly. But cloud shadows, it becomes a challenge. So developing this type of algorithms, it's quite a task by itself. Making use of some existing cloud mask data sets, that's probably will be the best shot. We won't be using any of this in this exercise. So what we will be using instead is just assumption or like very simple algorithm to say, to achieve the goal to get rid of the cloudy images, or maybe most cloudy images. And you can actually achieve this by, if you look at here, you see a red point on the middle of water body, which I just clicked to demonstrate this approach. If you click on this point, and in Earth Engine, it's very easy, of course, to plot values that you have over this point over time. So then we get a time series. Here I visualized, it doesn't matter which band you would use. So I used infrared band, I think. And if you show these values, how they change over time, that's the time series what we will see here. By the way, we use in this exercises, using, let's say, the satellite 2 imagery, we use top of atmosphere reflectance as a variables, so which usually changes between 0 and 1. And so when we plot these values, that's these values we will get. And you can see that they range between 0 and 10,000 because the Sentinel-2 data sets, images, they are scaled from, I think, 0 to, I don't remember, 26 or something thousand. This high values, so you have to divide it by 10,000, I think. So you see that this very high values, there's no way that this would be water in infrared band. So most of these values, what we see here, this is actually noise coming from clouds. But it's what is very useful when you work with this multi-temporal spatial analysis in Earth Engine, of course, is to plot histogram and look at this data like from different perspectives. So if you show histogram of this band, then we will get something what you see below. And if you look at this histogram, then we see that actually most of the values, they have quite low value. And so the noise what we get on top, we don't show like points there, but most of them, they actually somewhere in the tail, because this area is somewhere in Spain, I think, what I selected. And then what we have there is, so there are many sunny days as well. So the basic approach, what we can do is if we would compute this value, for example, from this point, query this value of this band from that selected point, and then set it as a property on every image, we could just use it to just filter out images where this value is high. So that's like trivial algorithm to get rid of cloudy images. And very also cost efficient, of course. So you don't query and do manipulations with every pixel and all bands. No, you just use one band, query values. Once we know how many images, what fraction we need to filter, we can get rid of most cloudy images, at least covering this pixel. And that's just basic operation in Earth Engine. How many images, what fraction we have to filter, that's also, it might be a challenging question. So there's one paper I included here in the slides. It's called Global 1 Kilometer Cloud Cover. Datasets was published in 2016 by Wilson, and it's actually used MODIS dataset to compute different statistics monthly, annually of clouds on Earth. And I actually use this data set quite a lot because it provides me statistics. Okay, how many images, if I take images over 1 year, for example, it answers question, how many images of those images are cloudy? So if your, let's say, the image acquisition times are relatively, let's say, distributed in the same way from year to year, so there are still many assumptions you would have to take into account, but for the recent years, this would be, let's say, valid method. And so by knowing this information, let's say by taking values of this one band in this case at specific location and just looking at these values, you could also say by knowing cloud frequency for this location, you could say that, okay, if my cloud frequency is 20%, then I would need to remove 20% of the brightest images from this area, from my image collection, out of my collection, and then I don't have to do any cloud masking, so they will be gone. And that's something what we will, okay, yes, here's an illustration for this approach. So basically, if you would compute some statistics which would correlate to cloud cover in this area of interest, then in our case it's just one pixel, but you could also take multiple pixels. If we take these values, sort them, then by knowing cloud frequency, we will be able to just remove or sort our images by this property that we computed this one of many locations. And then we will be able basically to get rid of cloudy images by applying simple filtering. But then knowing this threshold for how many images to filter, that would be the something that you can use to basically remove or filter out most cloudy images. And that's something what you will see in this step, in this code. And you see when we plot values of this infrared band over the same point, the time series looks much cleaner. So all high values images are gone. And so what we did is just applied filter. But parameterizing this with cloud frequency, that's might be, so it looks cumbersome maybe as at first, but what you see in this code snippet is basically querying it. This code queries this cloud frequency for this location, and then it applies that value of cloud frequency to filter out our images where we took images. For every image, we took value at one point, queried it, set as a property on every image, and then we filtered basically one fraction of, or computed threshold based on this all values and combined it with cloud frequency. So that's like very simple algorithm. And when we visualize this type images after this operation, this is what we will get. So imagine, or in this case, keep in mind that we just used 1 pixel to query these values. And what we see is that like most cloudy images, this covering this 1 pixel, they are gone. So we get relatively cloud-free time series. Here's just as example, looking back on the original time series. So we have cloudy images, but yeah, we used like basic algorithm to get rid of cloudy images. Then, of course, we can start doing any like land use studies, so computing, in this case, surface or normalized difference water index. We could use vegetation or any other for other studies. Or you could think of like doing this or kind of exercise, maybe not at 1 pixel, but maybe sample multiple pixels from multiple locations in this area, or even in every pixel if you really want to get rid of every cloudy image. So when we compute in NDVI, it's as I mentioned, it's like this would be the first step approach I would be using. And if you want to quantify, let's say, surface water area, of course, we would, after computing index, we would have to threshold it. In the theory, if you look at the original paper, you will see that the value is above 0, usually water, whereas below 0 is non-water. In practice, that's not always the case, but in case of this Spanish reservoir, where you have bright images, clean sky, or it's totally covered by cloud, this is more cherry picking. But zooming in somewhere in Asia, where you have like very humid atmosphere, working with these sensors, this threshold would change. But in this case, it would work quite nicely. So when we, the script, what you see under code, that shows basically what we do is just visualize values of this NDVI index. If you would visualize or threshold this index and then show our more binary image of let's say, where we would detect water, what you can see is that there is like many areas starting to pop up when we have shadows from hills, or even in some cases when we have clouds, then they start to show up in our time series. So this is basically demonstrates that this, there are sometimes false positives or false negatives when we have this area of water body covered by clouds. But what we can do as, let's say, once we threshold, let's say with just value is 0, we can just compute, of course, surface water area over this limited water body, and then we almost done a little bit more. The algorithm would look a bit more difficult than just processing GRC surface water mask, but this is basically the steps you would have to follow if you want to focus really on more accurate surface water detection studies. We can, in addition to NDVI, you could also combine, like compute the same type of water-ish index using different bands different from infrared. So take, for example, different shortwave infrared bands. Usually it's like a ratio between green and some infrared bands that would represent water. But there are, like in literature, multiple variation of that index available where you take shortwave infrared. I would not recommend using that in the snowy area, because that's basically inverted snow index, what you will get there. But if you want to really distinguish between different land use classes, then add in like multiple, in machine learning language terms, thinking like adding more features to really identify whether it's water body or it's maybe cloud shadow, that usually helps. And so if you look at the time series that we will get as a result using this approach, this is approximately what we will see for this water body. You can see here clearly that we see like water dynamics, even with single sensor like Sentinel-2, because this area is like 50%, I think, or 35% cloudy, we have enough revisit time to actually capture the water dynamics of this reservoir. We still get some noise, and in the next step we will see that basically by identifying what we get in these pixels and why we have noise there, so why these values really jump, then we will be able also to improve our algorithm. So in this slide, there is actually a script that, so if you click on that script, there will, on the code snippet, what I showed here, there's it demonstrates not surface water detection, but it's more code snippet, which shows one trick that I frequently use when I work with this data. So you can animate your images, that's one approach, but sometimes it's useful, like once you show some time series with values, to be able to click at the point and then visualize corresponding image to that time, or maybe that's different kind of property, and query it in Earth Engine and visualize on your map. And that's what this script or code snippets actually shows. So because Earth Engine, at least in code editors, there's also different events that you could react to. So in this case, what we will do here is once you add chart, on every chart you can actually react to the mouse click event. And what you will get as values there is a x-axis value of that point where you click. And that would, in our case, would correspond to time. So by taking that value, we will be able to basically grab the image which corresponds to this point and then visualize it on a map. So basically we can add our custom inspector. And that's, we will see, okay, this is the reason why this value jumps very high. Because in our area of interest that I used like rectangle to do analysis, we get many pixels which I think it's a cloud shadow in this case that detected as false positive water. And then suddenly area looks, which computed over this image is too high. So then what we can do is like to get rid of this noise. Of course, we see that the density of this time series of the actual water area is very small or very high compared to the noise. So we can do even like simple temporal filtering to get rid of these points. But another approach is what we could extend our cloud filtering algorithm by just adding, instead of using one point, so in this script example, I sampled basically multiple points of this area of interest. I think here I took like 50 points and basically computing the same statistics of, I think I still use like infrared band, but over 20 points. And when you use that instead of just one point in the middle of water body, what we will see is that our noise is gone. So we did not use any cloud masking here. We were able to get rid of cloudy images over our area of interest. And this algorithm, I believe it would also be applicable to many other areas or applications. And I think it's more, probably burns less CO2 or emits less CO2. If you look at, okay, is it actually practically usable, or should we use more advanced methods? But yeah, that's just one alternative way. And we can see that there is still some noise, but that's like, I would remove that using probably temporal filter. So yeah, compared to like our intermediate result to final result, that's hopefully will give you some new instruments that you can play with, but not just for water detection. The next step, what this slide shows, what we can do is by let's say compute this type of statistics or time series over multiple methods. Then the question comes, okay, can I actually combine time series computed using GRC dataset, image collection, and Sentinel-2 and Landsat, or merge them? There are like multiple ways to do this. You could harmonize all this data set to the same variable and then basically merge collections and treat them as single collection, keeping also track of the, let's say, as a property maybe for every image of where it's coming from which image collection. And another alternative is basically derive time series and then merge final feature collection representing our time series. Actually, I think here what I did is for every point of the Sentinel-2 image, I added basically the the GRC data set, so it's probably not the most efficient way. But my goal was to show, okay, what we just created from the Sentinel-2 image collection, is it actually, how does it perform compared to the more or less the state-of-the-art data set. Then we see that we, in this case, we created something which gives higher temporal resolution, and also we can see that there are, like at the low water level values in GRC data set, we get value is 0. The reason for that, if you would read the original paper, it states that when the analysis was done, the very low sun angle images have actually filtered out. And that results in that there's basically no observation for this point. So yeah, by combining this type of analysis, doing this analysis with multiple missions, multiple algorithms, you really kind of can compare it. And then if you have ground truth data, add in like in situ measurement, that would make sense as well. Then you could kind of reason about improvements or accuracy of your algorithm. Okay, I think this is last slide. I see we have actually 5 minutes, so I'm very good at timing. So let's see if there are any questions. I hope this was that was useful in some way. But yeah, feel free to look at the code and let's see if you have any questions.
And just to say, if you do have a question, come up to one of the standing mics, so that way it's recorded. Thank you.
No hands.
So there's no questions. You did a great job, Genna. Everybody's going to go home and be an expert at mapping surface water. Okay, before I have some.
You mentioned CloudScore Plus, and I'm wondering how you think that might compare when subtracting clouds.
Yeah, so the question is about comparison of CloudScore Plus to this approach. I think if we have CloudScore, I cannot answer, I did not test the CloudScore Plus. What I would assume that it's, I think I remember that looking at metrics or the accuracy, it's like one of the best, let's say from the accuracy point of view. I think you could, instead of just querying this infrared band values, you could query CloudScore Plus. If you have for every Sentinel-2 image, a CloudScore Plus image, that would be probably as efficient or more efficient. Whether you would want to query every point, or it would be sufficient to just sample CloudScore Plus values. Yeah, it would save some time probably, and you would have to do less manipulations with your raw data. Because basically CloudScore Plus, if you compare it to NDVI, which shows water probability, yeah, CloudScore Plus shows basically cloud probability. So it would make really a lot of sense to use this, in my opinion. Thank you for the question.
Yeah, I have a question about the NDVI and the NDVI when waters are like full of phytoplankton blooms or is intertidal areas with a lot of algae underneath. So have you compared these cases in which you don't have like it's not a false, it's maybe a false negative because it's water but it's full of vegetation?
Yes, so the question is actually, I think that's false negatives probably or positives I have in my results of reservoirs, which I mentioned before, because I did not account for that type of noise in this case. So if you're right that like if you have vegetation on top of water and your goal is not to compute vegetation area of water but your surface water area, this is something where you probably would make sense to combine this with some statistics from longer time, like this GRC water occurrence, for example, what computed over longer term. That would be useful data set to say, okay, this looks like a water body, and now imagine that we detected water, and then there is a part of pixels we don't see water. But looking at the historical data on like our prior, we would see, oh, there's actually, if there is water here and here, there should be water there as well. So this is like one of the approach I would use to get rid of this type of vegetation. But if your goal is to detect vegetation on top of water, then yeah, that would be a different story. And in terms of like different spectral indices, yeah, so I mentioned as like NDVI, if you have any presence of like vegetation or the sediment in the water, I know that the infrared band also will start to be more reflective. So this is type of application where you would really have to get deeper in analyzing all the signal from all bands, I would say, and maybe combining with even, so the machine learning algorithms. Thank you. Great question. Okay, if there are no any questions, I see our time is also up. And thank you a lot for joining this session. You can find me later, okay, to ask questions if there will be any. So thanks a lot. Hope it was useful.